The light that woke you this morning comes from a star that ignited 4.5 billion years ago, from a cloud of gas and dust. While the sun in your window might appear constant and eternal, this is merely a trick of perception. Our star has already traversed more than half its lifespan, and the transformations it will undergo are so profound that its current state of calm will one day look like its earliest infancy. I invite you on a voyage across billions of years, where every new chapter in this story is more remarkable than the last. Some 4.5 billion years ago, within one of our galaxy's spiral arms, a singular event unfolded that would permanently alter the destiny of this cosmic neighborhood. Picture a colossal nebula of gas and dust stretching for several light years, a distance greater than that to our closest stellar neighbor. Adrift inside this expanse were particles that were themselves ancient relics, each one a silent witness to cosmic cataclysms of a bygone era. And this is where the narrative becomes truly extraordinary. The material composing this cloud was anything but ordinary. In fact, every single atom of gas and speck of dust had previously existed deep within the cores of other stars. These elements had been forged in thermonuclear furnaces, endured the cataclysm of supernova explosions, and then journeyed across the cosmos for eons before congregating at the very location where our sun was fated to form. Just try to grasp the sheer scale of this gathering. If you could have witnessed this scene from a distance, you would have seen a vast, almost transparent cloud moving through the void of space. Within it, the temperature hovered just a few degrees above absolute zero, roughly minus 270 degrees Celsius. In such profound cold, it would seem that nothing could ever happen. But that assumption would be incorrect. For concealed within this frozen stillness was a force of immense power. Gravity. Every hydrogen atom and particle of dust exerted a faint pull on its neighbors, a force that was initially insignificant. But over the vast timescale of the cosmos, gravity worked relentlessly, acting like an invisible sculptor to gradually compress the nebula. This slow-motion contraction could have continued indefinitely, but a dramatic interruption was about to occur. A nearby star went supernova. Imagine a blast so powerful that in mere seconds it unleashes more energy than our sun will generate over its entire 10 billion-year life. The resulting shockwave tore through the serene nebula with the force of a tsunami crossing an ocean. Yet, this destructive wave did not obliterate the sun's future birthplace. On the contrary, it acted as the very trigger for its creation. The shockwave squeezed the cloud with such intensity that it began to collapse under its own mass at a staggering rate. What had once spanned light years was now compressed into a region the size of our solar system, and at this point, events began to accelerate dramatically. As the cloud shrank, its rotation sped up, much like an ice skater pulling in their arms to spin faster. The core became progressively hotter and denser as material plunged inward at incredible velocities, raising the temperature from the chill of deep space to thousands of degrees. Deep within this swirling chaos, the compressed gas and dust grew so dense that it started to emit its own light, glowing first a faint red, and then becoming progressively brighter. This was the birth of a protostar, an embryonic sun, hundreds of times larger than our current star, but not yet hot enough to ignite nuclear fusion. This nascent star was encircled by a swirling disk of residual material that continued to spiral onto its surface, a celestial turntable, playing not music, but a symphony of creation, from which all the planets, including Earth, would eventually form. The sheer amount of energy being released was staggering. Each second, immense streams of matter collided with the protostar's surface, with each impact delivering energy equivalent to a thermonuclear bomb. Like a cosmic newborn with an insatiable appetite, the young sun bulked up by consuming material from its surrounding accretion disk. The entire process, from the initial shock wave to the formation of this protostar, took only about 100,000 years, a mere instant on a cosmic clock. However, this glowing object was not yet a true star, as it shone only due to the heat generated by its gravitational contraction. The nuclear fusion processes that power stars for billions of years had not yet begun. To achieve that, the core needed to reach a critical threshold of 15 million degrees, which sets the stage for the most spectacular phase of our star's origin story. As the young sun continued to shrink under its own immense gravity, the temperature in its core steadily climbed past 10 million, then 12, then 14 million degrees. In this inferno, hydrogen atoms moved so rapidly that they started to bypass each other's electron shells, transforming the matter into a plasma, the fourth state of matter, where atomic nuclei and electrons are separated. Finally, roughly 10 million years after the initial collapse, the pivotal moment arrived. The temperature at the protostar's center hit the crucial 15 million degree mark, giving hydrogen nuclei the energy needed to overcome their mutual electrical repulsion and fuse together. In that instant, a true star was born. Thermonuclear reactions ignited, starting a cosmic engine that has been running non-stop for 4.5 billion years, converting 600 million tons of hydrogen into helium and pure energy every single second. And here is the most astounding part of this story. The very energy released in that moment of stellar birth is what warms your skin today. The photons of light that just reached your eyes began their long journey from the sun's core at a time before the simplest forms of life had even appeared on Earth, connecting you directly to that ancient fiery creation. Before the sun's light could ever reach your eyes, it spent 1 million years battling its way out from the star's dense interior. The sun had only just ignited, and it was a far cry from the serene star we observe now. It was destined for a volatile adolescence marked by cosmic fits of rage and planetary-scale destruction, a necessary phase that nearly extinguished any chance for life to begin in the solar system. The most amazing aspect of this cosmic history is that the events from 4.5 billion years ago, which unfolded in a remote cloud of gas and dust, are being replicated right now in countless other regions of our galaxy. Within the Orion Nebula, for instance, astronomers are witnessing stellar nurseries where hundreds of new suns are coming into existence. Every one of these infant stars is following the same developmental path as our own, and it's possible that around one of them, a planet could someday support intelligent beings who can reflect on their own cosmic origins. When the first thermonuclear reactions began deep within the protostar's core, there was no indication that our sun would one day nurture a living world. It was simply another star among billions, embarking on its immense life cycle from birth to eventual death. Yet, this particular journey would be filled with extraordinary events, with the most intense chapters still waiting to be written. Now that you understand the sun's origin, you can explore its chaotic childhood and turbulent adolescence, which will forever change how you see the tranquil star in our sky. If you believe the sun has always been the steady and reliable presence it is today, you are in for a significant revelation. The young star was a genuine celestial delinquent, holding the entire solar system hostage with its erratic behavior. Picture an adolescent, experiencing wild mood swings but powered by million-degree plasma, and venting its fury not with shouts, but with magnetic tempests powerful enough to scorch an entire planet. This initial 100 million year period of the Sun's life is what astronomers refer to as the T-Tauri phase, named after a class of young stars notorious for their intense volatility. Throughout this era, our star blazed with a brilliance 10 to 100 times greater than its current luminosity. But its brightness was not its most frightening quality. The young sun launched streams of charged particles with such incredible velocity that our modern solar wind is like a faint whisper in comparison. This was an unrelenting storm of protons and electrons moving at thousands of kilometers per second. Had a planet like Earth existed in its present state back then, this onslaught would have completely eroded its atmosphere within a few million years. Beyond this stellar hurricane, the Sun also unleashed solar flares so massive they make contemporary solar storms seem like minor sparks. Imagine an explosion releasing the energy equivalent to 1,000 years of all human civilization's consumption in just minutes. This was a regular occurrence for the young star. These cosmic outbursts were not chaotic accidents, but were caused by the young sun's inability to regulate its own magnetic forces. Its magnetic field lines would continuously twist and tangle into complex knots before violently snapping. This process released an amount of energy comparable to the simultaneous detonation of billions of thermonuclear bombs, all while the planets themselves were just beginning to coalesce from a disk of dust and rock. In this primordial chaos, fledgling worlds were little more than spheres of molten rock, under constant assault from asteroids and comets. It was into this environment that the hurricane-force solar wind swept, possessing the power to blow away the very atmospheres that were just starting to form. Consider the early history of Mars. Scientific evidence suggests the red planet once had a thick atmosphere, and perhaps even liquid oceans. That atmosphere was ultimately consumed by the young sun, scoured away by its intense solar wind, leaving the barren, frozen landscape we see today. This history presents a fascinating paradox that may alter your perspective on the sun's influence. The same stellar regression that condemned Mars likely became Earth's salvation. Our planet's closer proximity to the sun and its more robust magnetic field provided crucial protection. While the solar wind was unable to strip away Earth's atmosphere, it effectively created a shield that defended the inner solar system from far greater dangers originating in deep space. Reflect on the cosmic irony of this situation. The galaxy is awash with lethal radiation from supernovae, black holes, and other celestial cataclysms that could have easily sterilized any world where life was attempting to gain a foothold. However, our young and ferocious sun generated a protective cocoon around itself, using its powerful stellar wind to fend off these deadly galactic cosmic rays, thereby safeguarding the emerging planets. Roughly 100 million years after its formation, the sun finally started to settle. The thermonuclear processes in its core achieved a stable equilibrium, its magnetic fields grew more structured, and the solar wind subsided to more moderate levels. Our star had transitioned from a volatile teenager into a mature and dependable celestial body. This calming was a natural result of stellar evolution, as the continuous burning of hydrogen in its core altered the sun's internal dynamics. The massive convection currents that had once violently stirred its interior became more orderly, and the once erratic magnetic field adopted a much more stable arrangement. In a final, unexpected twist, this period of violent youth was fundamentally essential for the solar system to develop into the form we recognize today. The fierce solar wind not only shielded the planets from galactic radiation, but also cleared the inner regions of lighter gases, leaving behind the heavy elements required for the formation of rocky worlds like our own. Consider for a moment what the consequences would be if our sun had experienced a tranquil birth. For starters, our planet could have retained an atmosphere rich in hydrogen and helium, much like the gas giants, making life as we understand it impossible. Furthermore, without a powerful solar wind, cosmic radiation would have flooded our solar system, sterilizing any nascent organic molecules. Herein lies the brilliance of cosmic evolution, where phenomena that appear chaotic are actually fulfilling a crucial function, as the violent solar flares from our young star were not a bug, but a fundamental feature that established the necessary environment for intelligent life to eventually emerge. What's truly incredible is that we can still find evidence of the sun's tempestuous beginnings, as traces of its turbulent youth are preserved in Earth's most ancient rocks. Scientists have identified specific isotopes which could only have been created by incredibly potent cosmic radiation, markers akin to the scars on a seasoned warrior. Today, astronomers can witness similar adolescent turmoil by observing young, volatile stars in distant regions like the Orion Nebula. There, stars are undergoing the same developmental phase our sun did 4 billion years ago, violently ejecting streams of plasma and erupting with flares in a display of cosmic delinquency. However, one of the most surprising recent discoveries reveals that not every star endures such a chaotic adolescence. Stars with less mass than the sun can have a placid existence, whereas those more massive can exhibit even greater aggression. It seems our sun occupied a perfect middle ground. Its early life was just turbulent enough to forge the conditions for life, yet not so cataclysmic that it would have extinguished it. With that in mind, let's journey deep inside our star to understand the processes that have unfolded within its core for billions of years. Because the genuine wonder of the sun isn't found on its surface, but in its very center. As you appreciate a sunset or enjoy the warmth of the sun, an extraordinary event is taking place at our star's core. Picture a natural laboratory as large as our entire planet, where temperatures soar to 15 million degrees, and the pressure is 250 billion times more intense than what you experience on Earth. Inside this stellar furnace, a process that humanity has envisioned for millennia unfolds every single second. The conversion of physical matter directly into pure energy. Now, you should brace yourself for some figures that are truly staggering. Each second, deep within the sun's core, 600 million tons of hydrogen disappear completely. This isn't a burning process like wood in a fire. The hydrogen literally stops being hydrogen, converting instead into helium and a tremendous release of energy. To express this in more relatable terms, our star sheds a mass equal to 4 million tons every single second. This lost mass is transformed into the light, heat, and various other types of radiation that emanate from it. But that isn't even the most mind-boggling aspect of this process. This continuous, monumental detonation has persisted without interruption for the last 4.5 billion years. To truly comprehend the magnitude of what's occurring, try to imagine our sun unleashing the equivalent explosive power of all the hydrogen bombs humanity could manufacture over 1 billion years. Every single second. This mechanism that fuels our sun is known as the proton-proton chain reaction. And while the name might sound mundane, it describes what is arguably the most elegant chemical process in the entire cosmos. Within the hellish chaos of the solar core, 4 hydrogen nuclei, which are essentially single protons, come together and fuse to create one helium nucleus. I want you to pause and appreciate the sheer complexity of this event. Since protons all carry a positive charge, they naturally repel one another with immense force. For them to merge, this powerful electrical repulsion has to be surmounted, an act that is impossible under ordinary circumstances. But in the sun's core, the protons are moving at such extraordinary speeds that they can smash right through this electrostatic barrier. Now, listen closely, because this is where the true alchemy takes place. After 4 protons have fused together, a curious discrepancy appears. The mass of the new helium nucleus is slightly smaller than the total mass of the 4 protons that created it. So, what happens to this unaccounted-for mass? It is converted directly into energy, a principle described by Albert Einstein's celebrated equation, E equals mc squared. This lost mass constitutes just 7% of the proton's initial mass. And while that might sound trivial, when applied to hundreds of millions of tons of matter every second, it translates into an almost unimaginable quantity of energy. This is where our understanding gets turned on its head. The energy produced in the sun's core is unable to travel straight out, as the core is of such incredible density that a single photon of light might require 1,000,000 years to finally make its way to the surface. I want you to visualize this unbelievable odyssey. A photon originates deep in the sun's center, carrying the high energy of gamma radiation, but it is unable to move in a direct path. Every few centimeters, this photon smashes into an atom, gets absorbed, and is then shot out again in a completely random direction, a kind of cosmic-scale drunken stagger. Following 1,000,000 years of this haphazard journey, the photon at last arrives at the sun's surface. Its energy level dramatically decreased from potent gamma radiation into the gentle visible light that we see. And now for a final revelation that you probably won't see coming. The very sunlight that reaches your eyes today was actually created in the sun's core at the same time that the first multicellular life was emerging on Earth. That single photon has been a silent observer of the entire evolutionary history of complex life on our world, all while navigating the dense interior of our star. Considering that a photon's trek from the sun's core to its surface spans 1,000,000 years, you might wonder how quickly its brightness can change. The answer is that our star is remarkably stable. If the thermonuclear reactions at its center were to cease abruptly, we wouldn't know about it for 1,000,000 years, only when the last of the photons completed their journey to the surface. This is the brilliance of the sun's construction. Its immense mass functions as a colossal energy buffer, preventing it from flaring up like a match or extinguishing like a bulb, as any changes in its core are smoothed out over that 1,000,000-year transit. Even more remarkably, scientists have devised a way to look directly into the sun's heart without ever leaving our planet. This is accomplished using neutrinos, which are ghostly particles generated in thermonuclear reactions right alongside photons. Unlike light, these neutrinos slice through the sun's dense matter as if it were a vacuum, arriving at Earth in a mere 8 minutes. In fact, trillions of solar neutrinos are passing through your body every single second, completely harmlessly, because they almost never interact with matter. Yet, massive detectors, some the size of office buildings and buried deep underground, are able to capture a few dozen of these fleeting particles daily. Now, think about what researchers have learned by observing these solar neutrinos. They've discovered that the thermonuclear processes in the sun's core don't unfold exactly as our theories had anticipated. For many years, a significant puzzle baffled astronomers. We were only detecting about 1/3 of the neutrinos that our models predicted should be reaching us. This mystery, a genuine scientific detective story, persisted until physicists realized that neutrinos can actually morph from one type into another during their flight from the sun to Earth. Our star sends one kind, but some transform into other varieties that our detectors were unable to see. A finding that not only solved the puzzle, but transformed our grasp of fundamental physics. But the discoveries didn't stop there. Scientists also learned to perceive the sounds of the sun. Yes, that's correct. Our star resonates with sound waves that are generated in its depths and cause its surface to vibrate. Although these sounds can't travel through the vacuum of space, these solar quakes have enabled astronomers to construct a three-dimensional map of the star's interior. What this map reveals is a structure far more intricate than we ever imagined, with distinct layers, powerful currents of matter flowing between the poles and the equator, and even formations that resemble subterranean rivers of plasma. So, you now understand one of the sun's greatest secrets. Our star is far more than a simple burning ball of gas. It's an astonishingly complex machine, where every component is precisely balanced. A minor alteration in the core ripples through the star's entire structure, and events on its surface can inform us about what was happening in its heart 1,000,000 years prior. The sunlight warming your face at this very moment isn't new. That photon was born in the sun's core back when your distant ancestors were nothing more than single-celled organisms in an ancient sea. Let me paint a picture of that photon's incredible journey. It begins its existence at the star's center as a particle of immense energy, capable of blasting through any material. Yet, to this photon, the solar plasma is denser than the thickest fog imaginable. Every few millimeters, our light particle collides with an electron or proton, gets absorbed, and is then re-emitted in an entirely random direction. It's a journey that resembles a drunkard staggering through a mist. 1 step forward, 2 steps back, and 3 to the side. If it could travel in a straight line, it would reach the surface from the core in just 2 seconds. But instead, this random walk takes about 1,000,000 years to complete. What's truly astounding is how the photon itself is transformed by this endless voyage. It starts as lethal high-energy gamma radiation, but each collision with the particles of the solar plasma drains some of its power. Over time, the deadly gamma ray gradually weakens into X-ray radiation, then into ultraviolet light, and finally emerges as the gentle, visible light that sustains life on Earth. The most incredible part is that each photon's path is unique. One might escape to the surface in 100,000 years, while another could be trapped within the sun's depths for 10 million years, making its release a cosmic lottery. Imagine the sheer drama occurring within the sun's matter every second. Billions of photons are created by fusion and start their bid for freedom. Yet most are destined for an endless journey inside, transferring their energy to the surrounding plasma. This process heats the star and maintains the very temperature needed to sustain thermonuclear reactions. The sun is essentially a giant self-regulating system. If fusion reactions in the core speed up, the star expands and cools, which slows the reactions down. Conversely, if the reactions weaken, the sun contracts and heats up, accelerating them once again in a cycle that has maintained its stability for billions of years. And there's one final twist. Scientists have found that a photon's long path through the sun can be deciphered by the changes in its characteristics, as every collision leaves an imprint. By carefully analyzing the spectrum of sunlight, astronomers can figure out which layers of the star a photon has passed through and learn about the conditions in those layers 1,000,000 years ago. Just pause and consider that fantastic reality. We can actually observe the sun's ancient past simply by studying the light it radiates today. Every single ray of light holds data about ancient processes deep within the solar core, much like reading a star's personal history recorded in light. The narrative gets even more extraordinary when you consider that not all photons follow the same trajectory. The sun possesses a complex internal architecture with zones of differing densities and temperatures, meaning photons originating in various parts of the core traverse distinct layers and follow unique paths to the surface. In a truly astounding scientific achievement, researchers can now track individual photons and piece together their life stories. This has revealed that some rays bring us information about events that transpired in the sun's core 2,000,000 years ago, whereas others tell of happenings from just 100,000 years in the past. You can begin to grasp what a monumental shift this represents for astronomy, as we can now observe the sun's evolution in near real time, simply by examining light of varying ages. The experience is akin to viewing a cinematic story of a star's life, with each frame captured at a different point in its history. But the story takes an even more fantastic turn here. A portion of the photons escaping the sun today actually began their existence inside its core, before Earth's atmosphere even contained oxygen. These ancient particles have borne witness to the entire saga of life's emergence on our world, while undertaking their slow migration to the star's exterior. Another incredible fact is that a photon's trip from the sun's surface to Earth is completed in a mere 8 minutes. Following an epic journey of 1,000,000 years wandering through the solar interior, the last stretch is a mad dash at the speed of light. It's a journey comparable to a marathon runner breaking into an all-out sprint for the final 100 meters of the race. Now, consider the fate of these ancient photons upon their eventual arrival at Earth. They find their way into your eyes, get absorbed by plants undertaking photosynthesis, and contribute to warming the oceans and atmosphere. Energy that was born in a thermonuclear furnace 1,000,000 years ago ultimately becomes an integral part of life here. This concept reveals the genuine poetry of the cosmos. Every particle of sunlight is a messenger from the remote past, delivering the energy of primordial thermonuclear reactions and allowing us to literally subsist on light that predates many of the planet's own rocks. The tale of the photon, however, doesn't conclude at this point. Scientists have realized that any future transformations within the sun's core will only be revealed to us 1,000,000 years after they occur, once photons from those new reactions finally make it to the surface. In this way, the sun acts as a time machine, simultaneously showing us its history while concealing its future. With this knowledge of sunlight's true origin, I invite you to see our star in an entirely new light. That serene yellow orb is, in reality, a churning ocean of energy, where each ray is the product of a 1,000,000-year trek through a plasma inferno. We are all bathing in the glow of ancient light, largely oblivious to the incredible story behind every single photon. Now, brace yourself to discover that our seemingly placid sun can sometimes morph into an enraged monster, one capable of crippling our entire modern civilization with a single outburst. If your perception of the sun is that of a calm and dependable light in the sky, you should prepare for a major revelation. Our star leads a complex and emotional existence, with its moods fluctuating in cycles that astronomers have meticulously studied for centuries. And when the sun is in a foul temper, it can signal catastrophe for our technologically dependent world. Picture this. Roughly every 11 years, our star undergoes what could be described as a celestial nervous breakdown. Its magnetic field, which typically envelops its surface in a smooth pattern, starts to contort into knots, break, and reconfigure itself. This process creates dark blemishes the size of entire planets on the sun's surface and launches streams of charged particles into space, each carrying the energy of millions of atomic bombs. Now, it's crucial to pay close attention, because this is where the situation becomes truly dramatic. These dark patches on the sun, which astronomers have been observing for 400 years, are far more than simple cosmetic imperfections. Each spot represents a region where the star's magnetic field has become so severely twisted that it has literally ruptured through the surface. Inside a spot, the temperature is 2,000 degrees cooler than the surrounding areas, which is why it appears dark when contrasted against the brilliant photosphere. But hold on, that isn't even the most mind-boggling aspect. The sheer dimensions of these spots will force you to reconsider your entire understanding of solar phenomena. A relatively small spot can measure about 10,000 kilometers across, which is larger than the diameter of Earth itself, while the largest spots can swell to the size of Jupiter. Just try to envision a magnetic storm on the scale of a gas giant. And what's truly incredible is that these gigantic magnetic knots have their own distinct lives. They are born, they expand, they merge with adjacent spots, and then they vanish as though they were never there, with a full life cycle lasting anywhere from a few days to several months. This is the point where the situation can escalate dramatically. When the magnetic fields associated with sunspots become excessively entangled, an event known to astronomers as a solar flare can occur. In this process, magnetic field lines abruptly reconfigure, unleashing an amount of energy in just minutes that could power all of human civilization for 1,000,000 years. To help you grasp the magnitude of this event, the most powerful solar flares release energy equivalent to the simultaneous detonation of 10 billion megaton-class hydrogen bombs. Yet this isn't an explosion in the conventional sense of the word. It is a near-instantaneous conversion of magnetic energy into the kinetic energy of charged particles. Just pause and think about that. In a span of mere seconds, the sun flings billions of tons of plasma out into space at velocities reaching up to 3,000 kilometers per second. This projectile of plasma then hurtles through the solar system like a cosmic tsunami, overwhelming everything that lies in its way. And this is where the consequences become particularly compelling for us. When this wave of charged particles collides with Earth, a series of events unfolds that can seem like pure magic. The northern lights ignite, not just over the polar regions, but even in the tropics. Compasses start to point erratically, and radio communications are thrown into chaos across the globe. But all of this is merely a prelude compared to the potential devastation that could be inflicted upon our modern technological society. A solar storm of immense power could cripple our modern world, knocking out communication satellites, navigation, the internet, and even entire continental power grids. You could find yourself in a world suddenly thrown back in time, without electricity, mobile phones, or GPS. But here's the surprising part. This isn't just a future possibility. It's an event that has already occurred in our history. Back in 1859, our planet was hit by a solar storm so intense that the northern lights shimmered as far south as the Caribbean. Around the globe, telegraph systems went down, with some operators even reporting receiving electric shocks from their own equipment. This historic solar outburst was famously observed by astronomer Richard Carrington, who became the first person to witness and document a solar flare of such incredible magnitude aimed right at our planet. The frightening truth is that if a storm of that scale were to strike today, the economic fallout could reach trillions of dollars. Satellites would be fried by radiation, power transformers would overload, and the Global Positioning System, or GPS, would cease to function, potentially setting our civilization back centuries in a matter of hours. What's even more sobering is the discovery of far greater solar storms in our planet's distant past. By examining tree rings and ice core samples, scientists have unearthed evidence of a colossal event in the year 774 that was, by all indications, 10 times stronger than anything we've recorded in the modern era. Yet, here lies a profound paradox that may change how you think about solar activity. The very same phenomena that endanger our technological infrastructure are also crucial for the existence of life on Earth. The interaction between the solar wind and our planet's own magnetic field generates a protective shield, a bubble that wards off lethal radiation originating from deep space. So, how did scientists finally decode the Sun's 11-year cycle of activity? They discovered that our star's magnetic field functions like a colossal dynamo. Internal convective currents and the Sun's own rotation relentlessly twist the magnetic field lines, much like twirling spaghetti on a fork. This process culminates every 11 years in a complete reversal of the Sun's magnetic poles, where north becomes south and south becomes north. This magnetic flip is not a sudden event, but rather a gradual reorganization that coincides with the peak of solar activity. Picture a dramatic cosmic buildup. The magnetic field lines, contorted by the Sun's spin, get progressively more entangled. Eventually, the tension becomes unbearable, causing them to snap and violently realign, which in turn unleashes the immense energy we see as solar flares and coronal mass ejections. Remarkably, today's astronomers can now forecast solar weather. Dedicated satellites keep a constant watch on our star, and when a major flare erupts, we typically have a window of 8 hours to 3 days to brace for an incoming magnetic storm. An even more fascinating recent discovery is the profound connection between solar activity and our planet's climate. For instance, when sunspots virtually vanished in the 10th century, Europe was plunged into a mini ice age, a time when rivers froze solid, harvests failed, and Londoners famously skated on the River Thames. This leads us to contemplate what lies ahead. Although the Sun is in a relatively quiet phase at the moment, scientists caution that future superstorms are a certainty. It's a matter of when, not if. When that day comes, our high-tech society will confront the untamed force of the cosmos. But what you see on the Sun's surface is merely a fraction of the story, so prepare to delve into even deeper secrets. The most extraordinary phenomena happen far beneath the surface, where our star generates melodies that we are only now beginning to detect. You're about to enter a realm where scientific fact is more incredible than the boldest fiction. Because our sun is more intricate and enigmatic than any theorist ever conceived. It literally sings, and I mean that not as a figure of speech, but in terms of actual sound waves. The entire star, from its core outwards, is saturated with acoustic waves that make its surface pulse every 5 minutes. Envision a bell as massive as a star, with its surface heaving up and down by several kilometers in that short span. An oscillation of superheated plasma on a scale that dwarfs anything on Earth. So, what is the origin of these stellar sounds? The explanation is genuinely fascinating and lies deep within the sun, where constant convective motion takes place. Enormous currents of hot plasma ascend, while cooler plasma descends, and their collisions generate sound waves of immense power. To grasp the scale, consider that a single one of these convective cells is as large as Europe. When these continent-sized bubbles of plasma burst at the surface, they release acoustic energy that travels throughout the entire star. This is where the science becomes truly incredible. These sound waves don't simply disturb the sun's surface. They travel deep into its core, reflecting off different layers just like echoes bouncing off canyon walls. By studying these reflections, astronomers have successfully constructed a three-dimensional map of the solar interior. This groundbreaking field, known as helioseismology, is essentially the study of sunquakes. Using specialized telescopes instead of seismographs, scientists can listen to the sun, and through these vibrations, have discovered that its internal structure is vastly more complicated than our theories had ever suggested. You might be surprised to learn that the sun doesn't spin like a solid object at all. It features zones with varying rotational speeds, currents of matter flowing between its poles and equator, and even formations that resemble underground plasma rivers. Its equator makes a full circle in just 25 days, whereas its poles take a lengthier 35 days. And this differential rotation is the primary driver behind the tangling of its magnetic field, which in turn gives rise to solar flares. Helioseismology, the study of the sun's interior through its vibrations, has unveiled a distinct layer that astronomers have named the tachocline. This is a slim shell situated approximately 70,000 kilometers beneath the surface, marking the boundary where the fluid, differential rotation of the outer layers, gives way to the solid, unified rotation of the core. You can think of this boundary as a kind of cosmic meat grinder, where magnetic fields are stretched, twisted, and amplified by a factor of thousands, ultimately giving birth to the sunspots and flares that appear on the surface. Now, prepare yourself for a finding that compelled astronomers to completely rethink their models of stellar interiors. It appears the sun's core spins more rapidly than its outer layers, much like if Earth's own core were to outpace the rotation of its mantle and crust. Herein lies a profound puzzle, because the laws of physics dictate that friction should have synchronized the speeds of all the sun's layers eons ago. Yet, some unknown force has preserved this rotational difference for billions of years. What's more, the sound waves traveling through the sun do not move chaotically. Instead, they establish standing waves, akin to the resonance in an organ pipe. Our entire star operates as a colossal musical instrument, resonating with millions of distinct tones. Scientists have even managed to capture the sun's music by accelerating its sound oscillations 42,000 times, making them audible. The sound is an uncanny melody, reminiscent of the songs of whales or the howl of wind in the mountains. It is quite literally the voice of our star. Just imagine that this solar music is packed with information about the processes happening deep within the sun's center. Every single tone carries details about the star's temperature, density, and chemical makeup, allowing astronomers to interpret this sonic data almost like the score of a cosmic symphony. However, the most astounding revelation came when researchers started investigating solar tornadoes. Yes, you understood that correctly. The sun has tornadoes. But these are vortices not of air, but of plasma heated to 1,000,000 degrees, with dimensions comparable to the diameter of Earth. These plasma tornadoes ascend tens of thousands of kilometers above the sun's surface, rotating at speeds up to 300,000 kilometers per hour, while transferring matter between different strata of the solar atmosphere. This represents a true exhibition of nature's might, as a single solar tornado harbors more energy than all hurricanes in Earth's history combined. And incredibly, thousands of such tornadoes can be raging on the sun at any given moment. Another discovery that has transformed our perception of the solar atmosphere is the corona, a layer of rarefied plasma that extends far above the sun's surface and is heated to several million degrees. This makes it 300 times hotter than the star's surface itself, a paradox you can visualize by imagining the air above a campfire being hotter than the fire. For many years, scientists struggled to explain where the energy for such unimaginable heating could possibly originate. It turns out the solution to this mystery lies in the very same magnetic fields that generate sunspots and flares. Magnetic field lines emerging from the sun's interior continuously twist and annihilate one another within the corona, releasing an immense amount of energy in the process. These events occur on a scale that is difficult to grasp. Every second, a quantity of magnetic energy equivalent to the explosion of 1,000,000 atomic bombs is annihilated in the corona, and this is considered just a normal background activity. By now you are likely starting to appreciate just how complex and mysterious our home star truly is. What once appeared to be a simple sphere of gas is actually an intricately interconnected system, where magnetic fields dictate the movement of plasma, sound waves relay information between layers, and planet-sized tornadoes churn the atmospheric material. The most remarkable part is that all these processes have remained in perfect coordination for billions of years, functioning like an incredibly precise clockwork mechanism, where the smallest failure could spell disaster for the entire solar system. Everything we have covered so far, however, is merely the biography of the sun itself. It is now time to explore how our star has created, nurtured, and continues to oversee a complete family of 8 planets, hundreds of moons, and billions of asteroids. This is the narrative of how a single star assumed the role of architect for an entire world. Picture a scene from 4.5 billion years ago, when a disk of dust and gas revolved around the young sun, flat as a vinyl record but spanning a distance several times greater than Neptune's modern orbit. This disk contained all the material that would eventually coalesce into the planets, moons, and asteroids of our solar system. This is where the most extraordinary creation story in the universe unfolds, because the sun was not merely a passive light source at the disk's center. The young star was an energetic participant in the formation of the planets, as its gravity, radiation, and solar wind literally sculpted the emerging worlds like an artist shaping clay. And there's an even more intriguing element to this story. It turns out that the layout of the planets in our solar system is anything but random. The sun's radiation established distinct temperature zones across the early protoplanetary disk, which in turn governed what substances could solidify at various distances. Close to the star, the intense heat permitted only refractory materials like iron, silicon, and magnesium to exist. From these elements, the compact, rocky planets, Mercury, Venus, Earth, and Mars, were forged. Farther out in the colder regions, water ice and frozen gases were able to condense, providing the building blocks for the gas giants, Jupiter, Saturn, Uranus, and Neptune. Consider for a moment the remarkable precision of this cosmic assembly line. If our world had formed slightly nearer to the Sun, it would have ended up a scorched, rocky sphere, essentially a second Mercury. Conversely, had it been positioned farther away, Earth would have become a frozen wasteland where water remained perpetually solid ice. Instead, our planet settled perfectly within what astronomers define as the habitable zone. Now, for a twist you likely didn't see coming. The Sun didn't just form the planets. It continues to shape their destinies, every single moment. Let's look at Mars as an example. The red planet once boasted a thick atmosphere, and perhaps even oceans. However, its magnetic field was considerably weaker than Earth's, allowing the solar wind to gradually tear away its atmospheric blanket. This erosion persists to this day, with Mars losing approximately 100 grams of its atmosphere every second, carried off into space. Over 4 billion years, this relentless process has dwindled the atmospheric pressure on the Martian surface to just 1/16 of what we experience on Earth. Yet here lies a fascinating paradox. The very same solar wind that sealed Mars's fate ultimately became Earth's savior from a different kind of threat. Our world possesses a robust magnetic field that deflects the solar wind, forming a protective shield known as the magnetosphere. This bubble not only safeguards our atmosphere but also defends us from lethal galactic radiation. And what's truly incredible is that the Sun indirectly gifted Earth this magnetic field, as its powerful early solar wind heated our planet's interior so intensely that the iron core remains liquid even now, generating the magnetic field through convection. This is where the story gets even more compelling, because the Sun didn't just create the planets and then abandon them. Our star acts as a dynamic parent, constantly managing the climate, atmospheres, and even the internal structures of its planetary family. Take Venus, for instance. It is only 30% closer to the Sun than we are, but that seemingly minor difference was enough to ignite a catastrophic greenhouse effect. The surface of Venus sizzles at 460 degrees Celsius, making it even hotter than Mercury, which is much nearer to the Sun. Now, try to picture what awaits Earth as the Sun gradually brightens. Our star's luminosity intensifies by about 10% every billion years. In 1 billion years from now, this extrasolar radiation will initiate the same kind of runaway greenhouse effect that currently ravages Venus. Our oceans will boil away, transforming Earth into a desolate, hellish furnace. But the Sun's command extends beyond just planetary climates to their moons as well. Consider Europa, Jupiter's icy moon, which harbors a vast ocean of liquid water dozens of kilometers beneath its frozen crust. Where does the energy to maintain a liquid ocean so far from the Sun come from? The answer reveals an astonishing level of cosmic ingenuity. The Sun's gravity causes Jupiter to exert a fluctuating pull on Europa, stretching and compressing the moon as if it were a rubber ball. This constant internal friction generates heat, keeping the subsurface ocean from freezing over. This demonstrates the true scope of our star's influence, as it manages to control the oceans of a moon that orbits a gas giant 5 times farther away than Earth. Now, brace yourself for a discovery that compelled astronomers to completely rethink the sun's role in shaping the architecture of our solar system. It appears our star not only formed the planets, but also radically reconfigured their orbits on several occasions. Within the first 100 million years of the solar system's history, a cataclysmic event known as the Late Heavy Bombardment took place. Gravitational shifts caused by the migration of the gas giants sent billions of asteroids and comets hurtling toward the inner planets. This cosmic bombardment, which could have extinguished any nascent life on Earth, might have, paradoxically, been the very mechanism that delivered water and organic compounds to our world. Many of these comets and asteroids were essentially icy time capsules, carrying the frozen building blocks of life. What's even more remarkable is that the sun continues to shield the inner planets from asteroid threats. Today, Jupiter's immense gravity, anchored by the sun's own pull, functions as a celestial guardian, intercepting most hazardous objects before they can endanger Earth. Finally, the sun even affects how planets spin on their axes. The tidal forces from our star progressively slow the rotation of the planets, particularly those in close proximity. Mercury is already tidally locked, permanently showing the same face to the sun, much like our moon does to Earth. Venus rotates so sluggishly that its day is longer than its year, and our own planet's day lengthens by about 2 milliseconds each century due to these tidal effects from both the moon and the sun. The sun's gravity, in concert with Jupiter's, also maintains the chaotic orbits of the asteroid belt, preventing millions of rocky fragments from ever merging to form a new planet. It appears the sun and Jupiter function in tandem, like a pair of cosmic conductors, orchestrating a symphony of billions of celestial objects. The gravitational interplay between them is so intricate that it dictates the orbital path of every single asteroid and each particle of dust. Now, try to visualize what will unfold when the sun enters old age and expands into a red giant. Its gravitational influence will diminish, causing planetary orbits to widen and disrupting the delicate equilibrium that has kept our solar system stable for eons. In the ensuing chaos, planets could potentially collide or even be completely cast out into the void of interstellar space. However, that future is still incredibly distant. At present, the sun continues to act as a benevolent guardian for its planetary family. Every moment, our star radiates the light and warmth that not only make life on Earth possible, but also regulate the climates on all other planets and choreograph the movements of countless celestial bodies in a perfect cosmic dance. This brings us to the most enigmatic messengers that travel directly from the sun's core to us. These particles are so profoundly elusive that they can pass through the entire Earth as if it were empty space. Yet they are the very things that have unveiled our star's deepest secrets. As you absorb this information, about 100 billion of these invisible phantoms are streaming through your body every single second. Originating from the very center of the sun, they penetrate your skin, bones, and organs, exiting on the other side without the slightest indication that they have passed through anything at all. These particles are known as neutrinos, and they are the most remarkable spies in the universe. Consider a particle that possesses almost no mass, has no electric charge, and interacts so feebly with matter that it could traverse a wall of lead 1 light-year thick without ever registering the obstacle. To a neutrino, the entire planet Earth presents no more of a barrier than a fine mist does to you. Now, this is where the reality becomes truly fantastical. These ghostly particles are born in the sun's thermonuclear heart, at the same instant as photons of light. But in stark contrast to light, which takes 1,000,000 years to escape the sun's dense interior, neutrinos zip through the entire star in just 2 seconds. This means that neutrinos provide a direct, real-time account of the events happening right now inside the sun's thermonuclear furnace. While the sunlight you see today is a relic of events from 1,000,000 years ago, neutrinos deliver the latest news straight from our star's core. The challenge, however, is that neutrinos are almost impossible to catch. Of the trillions of these particles passing through your body each second, not a single one leaves a mark. To capture just a few neutrinos per day, scientists have had to build detectors the size of large buildings, filled with hundreds of tons of specialized materials. And these immense detectors are situated deep underground, often in abandoned mines or tunnels bored into mountains. This isn't because neutrinos are affected by depth, but to use the miles of rock overhead to shield the sensitive equipment from cosmic rays and other particles that, unlike neutrinos, cannot penetrate such a dense barrier. Imagine the intense drama that rippled through the scientific community when the first of these detectors began their work. They revealed that the sun was emitting only 1/3 the number of neutrinos that established theories predicted. This discrepancy puzzled physicists for decades, suggesting either that our understanding of the sun was wrong, or that something was altering the neutrinos on their voyage to Earth. So, picture the predicament. All theories of stellar evolution firmly stated that the sun should generate a specific quantity of neutrinos. Meanwhile, the detectors stubbornly registered only a fraction of that predicted amount. It was this contradiction that launched a true scientific detective story. Ultimately, the solution was not found with the sun or the detectors, but with the neutrinos themselves. It was discovered that these mysterious particles can actually transform from one type into another during their flight. The sun emits one specific kind of neutrino, but by the time they reach us, many have morphed into different types that the early instruments were unable to register. Just pause to appreciate the strangeness of this discovery. A particle so insubstantial it can fly through an entire star is capable of a complex metamorphosis, changing its very identity mid-journey. This led to an entirely unexpected twist. For neutrinos to be able to change, they must have mass, however minuscule it may be. And if neutrinos possess mass, their sheer numbers in the cosmos could mean they constitute a significant portion of dark matter, the enigmatic substance that makes up most of the universe's mass. Thus, in the process of studying messengers from the sun's core, scientists accidentally uncovered a major clue in one of the greatest mysteries of modern physics, suggesting neutrinos could be a key to understanding the entire universe. Let's return, though, to what these particles tell us specifically about our sun. Thanks to neutrino detectors, astronomers have, for the first time, peered directly into the star's heart and confirmed that the thermonuclear reactions are proceeding exactly as the theories describe. Moreover, neutrinos have revealed that the sun's core rotates as a solid body, unlike its fluid outer layers. What is truly astounding is that solar neutrinos have allowed scientists to measure the temperature at the center of our star with an accuracy of tens of thousands of degrees. That temperature is currently 15,600,000 degrees Celsius. Just think about the extraordinary precision of such a remote cosmic thermometer. Now, prepare for one final, even more incredible fact. Scientists have found that the flow of solar neutrinos actually changes with the seasons here on Earth. During the northern hemisphere's winter, when our planet is closer to the sun, we detect slightly more neutrinos. The difference is only a few percent, but its measurability is a testament to the remarkable sensitivity of modern detectors, which can register the subtle change in particle flow as Earth's orbit brings it a few million kilometers closer to, or farther from, our star. Did you know that neutrino detectors have uncovered something remarkable? It turns out that solar neutrinos reach us not just during the day, but at night as well. These nighttime particles originate from the far side of the sun and travel directly through our entire planet, as if it were nothing more than empty space. This extraordinary property means that neutrinos provide a way to monitor the sun continuously, even when it is hidden on the opposite side of the Earth, effectively eliminating the concepts of day, night, or weather for this branch of astronomy. Now, I want you to consider the incredible future that awaits neutrino astronomy. Scientists are currently developing next-generation detectors with the ability to not only confirm the presence of solar neutrinos, but also to pinpoint their exact origin. This breakthrough will pave the way for creating powerful neutrino telescopes, allowing us to view the cosmos through an entirely new lens and gather information previously beyond our reach. Beyond just observing the present, neutrinos also offer a glimpse into our sun's distant future. In approximately 5 billion years, our star's core will ignite new nuclear reactions, transforming helium into carbon, and these processes will emit neutrinos with distinct energy signatures. Future detectors will be sensitive enough to register these changes, essentially giving us an advance warning when this new stellar chapter begins. What this reveals is that neutrinos are far more than just abstract particles from the realm of theoretical physics. They are, in fact, practical instruments for unlocking the deepest secrets of stars. They empower astronomers to see into places no other form of radiation can reach, delivering real-time updates on the nuclear processes churning within cosmic objects. Knowing this, you can now look at the sun with a fresh perspective. While every photon of sunlight tells a story from 1,000,000 years ago, each neutrino informs us of what is happening inside our star at this very moment. At this point, it's time to dismantle one of the most enduring myths about our star, the idea that the sun is one of a kind. The truth is, there are billions of similar stars across the universe, with some being so close in nature to our own that astronomers refer to them as solar twins. So, what if everything you've been led to believe about the sun's singularity is actually just an illusion? Our star is a fairly common yellow dwarf among the 200 billion stars in the Milky Way, with about 10% of the galaxy's stars belonging to its class, giving us roughly 20 billion cosmic relatives. This is where the story gets really captivating. Astronomers have not just found stars that are similar to the sun. They have located its exact duplicates. These stellar doppelgangers share the same mass, temperature, chemical makeup, and age as our own sun. The variations are so minuscule that if an alien astronomer were to survey our galaxy from a distance, they would find it impossible to differentiate the sun from its twins. But the most astonishing part is that the hunt for solar twins is far from a mere astronomical novelty. It's a profound scientific mission. By examining stars that are like our sun but at different stages of their lives, Astronomers can piece together the complete evolutionary journey of our star, from its formation to its eventual demise. This brilliant strategy allows you to witness our star's past by finding an identical twin a billion years younger, or to preview its future by discovering a twin a billion years older. And when astronomers began their systematic search for these solar analogs, they found that youthful versions of our Sun are considerably more energetic and volatile. Stars that are a billion years old erupt with flares tens of times more powerful than the Sun's current activity, and their magnetic fields are intensely turbulent. In contrast, older solar twins are substantially more placid than our star, with their magnetic activity having almost completely subsided, their flares being exceedingly rare, and their rotation having slowed down significantly, indicating our Sun is truly in the prime of its stellar life. What makes this even more intriguing is that among these solar twins, astronomers have identified stars with planetary systems that bear a striking resemblance to our own. Some of these systems feature rocky planets within the habitable zone, gas giants orbiting farther out, and even familiar-looking asteroid belts. This raises a possibility you likely didn't anticipate. If these planetary systems mirror ours, it's plausible that life could have also arisen on the planets orbiting these stars. Consider the implications if one of these solar twins is older than our Sun. Life on its planets could have had a billion-year head start, potentially reaching a far more advanced stage of development. You can just imagine a civilization somewhere in our galaxy orbiting an exact copy of our Sun that has had an extra billion years to evolve. Such a civilization would already understand its star's destiny, because it could observe younger solar analogs like our own Sun. Yet a paradox emerges. Despite the billions of potential solar twins in the universe, scientists have managed to identify only a few dozen precise matches so far. The reality is that even the most minute deviations in mass, chemical composition, or age can dramatically alter a star's evolutionary path. And the most incredible finding from this search is that the more closely astronomers examine these twins, the more they appreciate our own star's distinctiveness. It appears our Sun possesses an unusually stable luminosity when compared to other stars in its class. While our star's brightness varies by mere fractions of a percent, many similar stars exhibit fluctuations of several percent. Just try to picture the consequences if the Sun were less consistent. Brightness swings of just a few percent would trigger catastrophic climate shifts on Earth, with ice ages and periods of intense global warming alternating every few hundred years, which would make the evolution of complex life forms utterly impossible. This realization has compelled astronomers to entirely rethink how prevalent life might actually be in the universe, suggesting it requires not just the right kind of star and a planet in the right place, but also a star with exceptional stability. A star must also maintain exceptional stability for billions of years. Now brace yourself for a revelation that will reshape your perspective on the Sun's position in our galaxy. As it happens, our star resides within a highly specialized area of the Milky Way, a region that astronomers have designated the galactic habitable zone. Getting too close to the galactic center is perilous, with its intense black hole radiation and frequent supernova blasts. Yet, on the distant periphery, there is an insufficient supply of the heavy elements needed to form rocky worlds. Our Sun is situated perfectly in this galactic sweet spot, a location that offers enough heavy elements without an overwhelming amount of lethal radiation. Furthermore, the Sun's path around the galactic core is almost a perfect circle, which has kept our solar system in a comparatively safe harbor for billions of years. In contrast, many other stars trace elliptical orbits, which periodically plunge them into hazardous zones teeming with high-energy radiation. But astronomers have uncovered something even more remarkable. The Sun travels through the galaxy at an incredibly precise velocity. It moves in perfect lockstep with the density wave that creates the Milky Way's spiral structure, never falling behind or surging ahead of the galactic arms. This reveals that the Sun is anything but an ordinary star among its billions of peers. It is an extraordinarily steady celestial body, inhabiting an ideal galactic neighborhood and following a perfect orbit, all of which create the ideal conditions to support life on its planets. Now, think about what this means for the search for extraterrestrial life. Astronomers aren't merely seeking planets around stars that resemble the Sun. Their search is far more specific. They are looking for worlds orbiting stars that mirror our own in their stability, their galactic address, and their entire evolutionary timeline. These efforts show that the rise of intelligent life appears to depend on an astonishingly lucky alignment of many different factors. It's not enough to have a suitable planet. You also need a uniquely stable star in an exceptionally favorable part of the galaxy. Such cosmic real estate is much rarer than you might imagine. This, however, doesn't mean we are necessarily alone. The universe is home to trillions of galaxies, and each of those contains billions of stars. So even if the prerequisites for life are incredibly uncommon, the sheer number of potentially habitable worlds could still reach into the millions. With this knowledge about solar twins and the distinctiveness of our own star, you can gain a fresh appreciation for the marvel of your own existence. You are living next to a star of exceptional consistency, one that has fostered ideal conditions for life's evolution over billions of years. This is a staggering stroke of cosmic luck, turning every single day of your life into a genuine gift from the cosmos. But prepare yourself for an unforeseen development. This golden age of stability and life is not destined to last forever. The Sun has already started its aging process, and the initial indicators are detectable right now, provided you know where to search. Our star is on a slow but certain path toward a midlife crisis that is set to fundamentally alter the entire solar system. Even as you listen to my voice, changes are unfolding deep within the Sun's core that, in a billion years, will make Earth completely uninhabitable. Every second, our star fuses 600 million tons of hydrogen into helium. And this helium isn't going anywhere. It's building up at the star's very center, much like ash in a fireplace. Now, listen closely, because this is where the story takes a dramatic turn. Across 4.5 billion years, a massive amount of helium has accumulated in the Sun's core. It now constitutes roughly 60% of the star's central mass. This dense helium ash causes the core to slowly compress under its own immense weight. Yet, here lies the paradox that will challenge your ideas about stellar aging. As the core contracts, it gets hotter, which in turn makes the thermonuclear reactions even more ferocious. An aging sun, it turns out, does not grow dimmer. It becomes brighter. The luminosity of our star increases by approximately 1% every 100 million years. To grasp the magnitude of this change, consider that since life first emerged on Earth, the Sun has become 25% more luminous. The paradox is that 4 billion years ago, when life began, our star was so faint that Earth's oceans should have been frozen solid. This didn't happen because the young Earth was shrouded in a denser atmosphere with a powerful greenhouse effect. And now for a twist you likely didn't see coming. This very same process of steady brightening is what will ultimately lead to a future catastrophe. In 1 billion years, our star will shine 10% more brightly than it does today, and that extra heat will initiate a runaway greenhouse effect on Earth. This is how it will play out. The more luminous sun will start to evaporate the oceans at an accelerated rate. Since water vapor is a potent greenhouse gas, the atmosphere will trap more heat, which will cause even more rapid evaporation. This feedback loop will become self-sustaining until, eventually, Earth's oceans will have boiled away entirely. The water vapor will ascend to the upper atmosphere, where ultraviolet radiation will split it into hydrogen and oxygen. The lighter hydrogen will escape into space, and the oxygen will react with the planet's rocks, transforming our world into a scorched, desolate wasteland, much like modern-day Venus. And perhaps the most terrifying aspect of this future is that, on a cosmic scale, 1 billion years is not a long time. It represents only a quarter of the sun's remaining lifespan. This implies that for the vast majority of its future existence, our star will shine down upon a dead Earth. But wait, this isn't the only symptom of our star's advancing age. Astronomers have found that the sun is also gradually losing mass, not just from converting matter to energy, but also through the solar wind. Each second, our star casts about 1 million tons of its own substance out into space. Over the course of its existence, the sun has shed a mass comparable to that of our own planet through the solar wind. While this is a tiny fraction of the star's total mass, even this slight loss influences the orbits of the planets. As the sun's mass decreases, its gravitational influence diminishes, causing the planets to slowly spiral away from the system's center. Now, I want you to consider another, more subtle aging mechanism. As helium builds up in the sun's core, the divide between the core and its outer layers grows more distinct. Hydrogen now burns within a thin shell enveloping this helium core, leading to an increasingly volatile stellar structure. From this point, the situation begins to rapidly escalate. In approximately 5 billion years, the hydrogen fuel in the sun's core will be entirely depleted. At that very moment, thermonuclear fusion within the core will halt, prompting it to contract swiftly under its own immense gravity. The temperature at the star's center will surge to a staggering 100 million degrees, igniting new nuclear reactions that transform helium into carbon. However, these new fusion processes behave very differently from hydrogen burning. They ignite in erratic, unstable bursts, which will cause the entire star to throb like a colossal heart. Now, this is where the story takes a truly incredible turn. The sun's outer layers, no longer held up by the pressure from the core, will start to collapse inward. Upon reaching the hydrogen-burning shell around the helium core, they will trigger a thermonuclear blast of immense power. This cataclysmic explosion will violently propel the star's outer layers outward again, forcing the sun to expand to previously unimaginable proportions. Our star will transform into a red giant, swelling to a diameter that surpasses the orbital path of Mars. But you should know that this moment remains in the distant future. For now, we are only witnessing the earliest, almost imperceptible indications of our star's aging. The most dangerous characteristic of the sun's aging is its slow and unnoticeable progression. Variations in luminosity of just fractions of a percent occurring over millions of years are impossible for you to perceive within a single human lifetime. Yet, these minute shifts compound over time and will, sooner or later, culminate in global catastrophes. Now, think about how this affects our search for life across the cosmos. It suggests that even if life arises on a planet orbiting a star like our Sun, it faces a strict deadline to evolve into an intelligent species. Biological evolution is in a race to produce intelligence before the star ages and makes the planet uninhabitable. What's even more remarkable is that Earth seems to have joined this cosmic race at the last possible second. If intelligent life had appeared on our planet a billion years later, it would have been confronted with a climate disaster driven by the sun's increasing luminosity. You and I exist within a fleeting golden age, a brief interval between the rise of complex life and the beginning of our star's decline. Modern astronomers can study aging solar counterparts in other regions of our galaxy, and these stars offer a glimpse into the sun's destiny. Their planets have already endured climatic apocalypses, with oceans that have boiled off and atmospheres that have been stripped away into space. Yet surprisingly, some of these dying systems exhibit signs that advanced civilizations may have tried to ensure their survival by moving to more distant planets and moons. Astronomers have observed peculiar fluctuations in the light spectra of these stars, which could be evidence of the activities of highly developed societies. So, I want you to grasp the challenge that humanity now confronts. We have roughly 1 billion years to either master the ability to regulate the sun's brightness, or to devise a method for migrating to a new star system. On a cosmic scale, this is an incredibly short period, but it might just be sufficient for the necessary technological advancements. Some scientists are already proposing concepts to prolong the sun's lifespan, such as projects to extract the helium ash from its core, or to introduce a fresh supply of hydrogen. It may sound like pure fantasy, but who can predict what a civilization could accomplish with 1 billion years of continued development? Now you are aware of the fundamental secret of our era. We are living in the prime of the sun's life. But this peak is already tipping into a long decline. Every day you enjoy under the light of our star is a day drawn from a finite reserve of time granted to Earth within the habitable zone. But you shouldn't fall into despair just yet, because even more spectacular events are written in the sun's future. Its transformation into a red giant is merely the prelude to the most fascinating chapter in a star's existence. In 5 billion years, the sun will experience a metamorphosis so profound that our current star will appear as a mere infant by comparison. Imagine a star growing to be 200 times larger and thousands of times more luminous than the sun you see today. A celestial body that will consume Mercury, Venus, and quite possibly Earth. Welcome to the age of the red giant. Now, you must prepare for the most climactic phase in our star's life story. The familiar, tranquil yellow star that has nurtured Earth for billions of years will morph into a crimson behemoth, one capable of swallowing entire worlds. This won't be a slow, steady transformation, but a true cosmic disaster that will completely reshape the solar system over just a few million years. When the hydrogen in the sun's core is finally used up, an event known to astronomers as the helium flash will take place. I want you to picture a thermonuclear detonation, not occurring on the star's surface, but deep within its very center. In a matter of seconds, the core temperature will spike to 150 million degrees, unleashing an amount of energy equivalent to the output of our entire galaxy. But here lies a great paradox. This monstrous internal explosion will have almost no visible effect on the star's exterior. The tremendous energy from the helium flash will be absorbed by the sun's immense mass, much like thick walls muffle the sound of a blast. A distant observer would likely only detect a minor increase in its brightness. Now, pay close attention, because this is where the process becomes truly captivating. Following the helium flash, the sun's internal structure will be radically altered, with a small but extraordinarily hot core at its center, where helium will begin its conversion into carbon. Imagine the sun's future structure. A dense core the size of Earth will be enveloped by a thin, hydrogen-burning shell, which is itself surrounded by an immense, expanding atmosphere of cooling gas. This new celestial body will feature a core 1,000,000 times denser than water, a fiercely burning shell just a few thousand kilometers thick, with temperatures in the hundreds of millions of degrees, and an atmosphere so rarefied across hundreds of millions of kilometers that it's practically a vacuum. This configuration is inherently unstable, as the erratic burning of hydrogen within the thin shell will cause the star's outer layers to repeatedly expand and contract. The sun will begin to throb like a massive heart, with each pulse lasting several months. With every one of these pulsations, you can picture the star's atmosphere accelerating outwards at tens of kilometers per second, before collapsing back toward the center. Much like Earth's own atmosphere launching into space only to crash down again. Now, try to grasp the sheer scale of this red behemoth. At its peak size, the sun will have expanded beyond the orbit of Mars. If you could witness this transformation in our current solar system, you would see Mercury and Venus become completely engulfed by the star's atmosphere, where they would be instantly vaporized and consumed. However, the star's colossal size isn't even its most shocking attribute. This red giant will also be incredibly luminous, shining with 1,000 times the sun's current brightness. Its light will shift from the familiar yellow to a deep blood-red hue as the surface of the swollen star cools to 3,000 degrees. Just picture a crimson sun filling half the sky, pulsating like a living creature, and bathing the solar system in a sinister, reddish glow. A scene of true cosmic horror. At this point, the fate of Earth becomes truly hellish. If our planet still exists, its surface temperatures will climb to 1,500 degrees, and its oceans will do more than just boil. They will completely evaporate and escape into space, while the atmosphere is scoured away by the powerful stellar wind. Yet, in a fascinating twist, the outer worlds like Jupiter, Saturn, Uranus, and Neptune will experience entirely new conditions as the red giant's radiation melts their icy moons, creating vast oceans of liquid water. Think about this extraordinary cosmic irony. At the very moment Earth is being rendered a molten ruin, the moons orbiting Jupiter and Saturn could transform into new, potentially habitable worlds. Icy bodies such as Europa, Enceladus, and Titan will receive sufficient energy to perhaps foster the development of life on their newly formed ocean surfaces. Then comes the most climactic moment in the red giant's history. After approximately 100 million years of these pulsations, the star will achieve a critical instability, casting its outer layers into space through a series of explosions, each one more powerful than all of humanity's thermonuclear weapons combined. This process won't be a sudden blast, but a slow, gradual shedding of its outer shells over thousands of years, causing the star to become progressively smaller, hotter, and more stable. What is most profound about this process is that the red giant's death is also an act of creation. The ejected material is enriched with heavy elements like carbon, oxygen, and neon, all forged by nuclear reactions inside the star. These elements will go on to become the fundamental building blocks for the next generation of stars and planets. Consider what will happen to the remaining planets during this stellar apocalypse. Any worlds that avoid being consumed will be pummeled by streams of hot gas moving at hundreds of kilometers per second, stripping their atmospheres, reshaping their surfaces, and throwing their orbits into chaos. But surprisingly, the moons of the gas giants, now with liquid oceans, may retain them even after the star shrinks. And although these oceans will freeze, life could potentially survive beneath the ice. Here is a turn you probably did not anticipate. The red giant phase is not merely destructive, but also a source of incredible opportunity. If humanity's descendants survive, they will have access to immense energy resources from a star that emits thousands of times more power than our sun today. An advanced civilization could treat the red giant as a colossal power station and mine, or even construct a Dyson sphere to harness more energy than our galaxy has produced in 1 billion years. Even if no one is there to harness its power, the sun's transformation into a red giant will be one of the most stunning spectacles the cosmos has to offer. This engorged star will be visible from thousands of light years away, serving as a brilliant beacon in the interstellar darkness. You now have a picture of the most turbulent era in our star's biography. The sun will not simply burn out. It will unleash a final, magnificent display that will remake the entire solar system, signaling both an end and a new beginning. But this phase is still not the conclusion of the story. The final act of this stellar drama will see the dying star create one of the most beautiful phenomena in the entire universe. After the red giant finishes casting off its outer layers, a tiny, yet extraordinarily hot core will be left behind at the center. Expanding around it will be a glowing cloud of gas, which will form the breathtaking celestial object that astronomers refer to as a planetary nebula. I want you to envision the final act of a dying star, which is poised to become one of the most spectacular displays in the entire cosmos. As the red giant concludes the process of casting off its outer atmosphere, a truly extraordinary event unfolds. The star's exposed, intensely hot core will flood the surrounding clouds of expelled gas with ultraviolet light, causing them to ignite with a brilliance akin to colossal neon sculptures. This isn't a violent explosion or a disaster. Instead, it is a celestial symphony of light destined to play out over tens of thousands of years. Now, let's address a misconception that might reshape your entire view of stellar death. Planetary nebulae are completely unrelated to planets. This confusing name has its roots 300 years in the past, when astronomers first aimed their telescopes at these formations. To them, the luminous, rounded disks looked like far-off planets. But the reality is that they are observing the beautiful remnants of a star's final moments. Effectively, a stellar graveyard. To grasp the sheer magnitude of this event, consider that the gas cloud from our own dying sun will expand outward at a rate of 20 kilometers per second. After 10,000 years, this expanding shell will have grown to more than a light year across, a distance 60,000 times greater than the orbit Pluto currently occupies. This scale transforms our solar system's end into a truly galactic phenomenon. Yet what's even more breathtaking than the size is the intricate beauty of the planetary nebula. At its heart, The scorching core radiates ultraviolet light with a temperature soaring to 100,000 degrees. This invisible light energizes the atoms within the gas cloud, compelling them to emit light in specific colors. Hydrogen glows a deep red, oxygen shines in green and blue, and nitrogen contributes a violet hue. The result is a cosmic rainbow that spans light years in diameter. This luminescence is far from random. It arranges itself into complex patterns of rings, spirals, and jets of gas, with each detail chronicling the star's turbulent final days. You could say that a planetary nebula serves as the star's own self-portrait, rendered using the very essence of its own light. Each structure is a unique artistic statement written across the fabric of space. And here is where the subject becomes truly fascinating, so I need your full attention. The final form of a planetary nebula is determined by the specific way in which its parent star perished. A nebula will appear perfectly spherical if the red giant managed to shed its outer layers uniformly in all directions. However, if powerful stellar winds were channeled along the star's poles, the result is a bipolar nebula with a distinctive hourglass shape. Some of these celestial objects bear a striking resemblance to the eyes of cosmic beings, while others appear as ethereal butterflies or blooming flowers. Astronomers have catalogued nebulae shaped like rings, spirals, and even one that eerily resembles a human skull. Each of these forms represents the star's departing signature, its personal and final farewell to the universe. What makes these cosmic masterpieces even more remarkable is their visibility across immense cosmic distances. The planetary nebula produced by our own sun will shine more brightly than a great many stars in the night sky, making it observable even from adjacent galaxies. The end of our star will effectively create a celestial beacon, one that astronomers on distant worlds could study for millions of years to come. This is where the beauty of the event moves beyond simple visual appeal. Planetary nebulae are much more than just stunning images from deep space. They function as natural laboratories where new chemical elements are forged. Inside the nebula, the superheated core continues to drive nuclear reactions, synthesizing elements that are heavier than iron and seeding the cosmos with new materials. Now, I want you to picture what astronomers refer to as stellar rain. The ever-expanding cloud of the planetary nebula will eventually merge with the surrounding interstellar gas, enriching it with the heavy elements created at its core. In time, new generations of stars and planets will coalesce from this newly enriched material, continuing the cycle of cosmic birth. In this way, the death of our sun becomes an incredible act of cosmic generosity. All the carbon, oxygen, and other vital elements forged in the heart of our star will be dispersed throughout the galaxy, providing the essential building blocks for worlds yet to be formed. It's entirely possible that on a planet orbiting one of these new stars, life will one day arise. Life constructed from the very atoms born in our sun. There is a poignant paradox to this splendor, however. The most visually stunning planetary nebulae are quite ephemeral on a cosmic timescale. Within about 100,000 years, the gas will have dissipated too far into space. The core's ultraviolet radiation will have faded, and the magnificent glow will dim forever. All that will be left of this grand spectacle is a tiny, incredibly dense stellar remnant, known as a white dwarf. But just when you think the story is over, there's a development you likely didn't anticipate. The entire process of forming a planetary nebula can happen more than once. If the original dying star was part of a binary system with a companion, the resulting white dwarf can begin to siphon material from its neighbor. This can cause it to swell up and cast off its outer layers all over again, creating a new nebula. These recurring planetary nebulae give rise to some of the most intricate structures found in space, including concentric rings, complex spiral patterns, and interwoven streams of gas. They are often compared to cosmic roses, with each delicate petal representing a distinct episode in the star's prolonged and dramatic death. What's even more profound is the critical function planetary nebulae serve in the chemical evolution of our galaxy. If it weren't for them, the universe would lack sufficient oxygen to form water, carbon to build organic molecules, and nitrogen to create proteins. This reveals that the death of a star is not a conclusion, but rather the necessary precursor to new life. Try to imagine what astronomers in the far future will witness when our sun's planetary nebula finally illuminates the void. They will likely see a gorgeous, symmetrical formation with a hot white dwarf at its center, encircled by glowing rings of gas shining in every color imaginable. These distant observers might attempt to figure out what kind of star could produce such a wonder. By analyzing the nebula's chemical makeup, they would likely deduce that a star very much like their own once thrived in this region of space. It's even plausible that they could detect faint traces of the planets that once circled this long-dead star. This cosmic forensics would allow them to piece together the history of our solar system, long after it has vanished. But perhaps the most incredible possibility is that some evidence of life from our solar system could persist within the nebula itself. If humanity, or whatever we evolve into, constructs vast, durable cosmic structures, the remnants of these projects might appear in the nebula's spectrum as unusual concentrations of rare elements. This would be our lasting signature. This means a planetary nebula is not merely a star's tombstone, but also its memorial. It's a method for our sun to communicate across eons, telling future cosmic civilizations that a stable star once burned here, and that around it, life may have had a chance to flourish. The nebula becomes the final chapter of our story, written in light. So now you understand the nature of the sun's final breath. It will depart from the universe in a blaze of glory, generating one of the most awe-inspiring phenomena known to exist. Ultimately, its death will be a profoundly creative act, enriching the cosmos with new elements, and potentially seeding the galaxy with the promise of new worlds and new life. The story, however, does not conclude with the planetary nebula. At the heart of this celestial spectacle, the remnant of our sun, a minuscule yet tremendously dense star, will begin a long, slow process of cooling. Its lifespan will far exceed the current age of the entire cosmos, marking a new, incredibly enduring chapter. After all the violent upheavals and cosmic light shows, you should understand that what remains of our magnificent sun will be a tiny star, no bigger than Earth, yet containing nearly all of its original mass. This is a white dwarf, a kind of zombie star fated to glow for trillions of years. Consider the sheer paradox. Long after every other star in the universe has extinguished, this planet-sized object will be so dense that a single teaspoon of its substance would have the mass of an elephant. This material exists in a state found nowhere else in our solar system, where electrons are compressed so intensely they generate a pressure strong enough to support the weight of a whole star within the confines of a planet. But the most remarkable part is its birth. The white dwarf will emerge with a surface temperature of 100,000 degrees, making it as hot as the most brilliant stars in the sky. It will radiate with a brilliant white light, which is how it gets its name. But without any internal fuel source, it will gradually cool, like a glowing coal cast into the emptiness of space. The numbers involved in this cooling process are truly staggering. During its first billion years, the white dwarf will drop from 100,000 to 50,000 degrees. Over the following billion years, its temperature will halve again, from 50,000 to 25,000 degrees. Beyond that point, however, the cooling slows down dramatically, requiring more than 1 trillion years for it to reach the current temperature of our Sun. To put these time frames into perspective for you, 1 trillion years is 70 times the entire history of the universe up to this point. By the time our Sun's white dwarf has cooled enough to potentially support a habitable planet, the cosmos itself will be 70 times older. All conventional stars will have long gone dark, galaxies will have scattered, and the universe will be a profoundly cold and empty place. This is where the narrative takes a surprising turn, as white dwarfs are the most long-lived objects in existence. They will be the final beacons of light in a dead universe when not a single ordinary star is left shining, tens of trillions of years into the future. Imagine the opportunities this endurance presents. Any civilization that survives into this era would have access to energy sources that outlast matter as we currently know it, offering power on a truly cosmic scale. What's even more astounding is that some white dwarfs might retain their planets. If a world can withstand its star's transformation into a red giant and the subsequent expulsion of the planetary nebula, it could continue to orbit the stellar remnant. Although this planet would be a barren, lifeless rock, its existence could stretch on for trillions of years. In fact, astronomers have already confirmed the existence of planets orbiting white dwarfs within our own galaxy. These surviving worlds have endured the death of their stars and now circle the cooling embers. Remarkably, some even possess atmospheres made from gases that were once part of the star itself, a completely unexpected discovery. It appears that a star's death isn't an end for its planetary system, but a transformation, allowing planets to outlive their parent star and begin a new, incredibly long life alongside a white dwarf. Now, picture a white dwarf with a companion star. The dead star's immense gravity can siphon material from its living partner, and once enough matter has been collected, it can trigger a thermonuclear blast on the white dwarf's surface. This event, known as a nova, can cause the white dwarf to shine 100,000 times more brightly for several days. From our vantage point on Earth, it would seem as if a new star had suddenly appeared in the heavens. This flash, however, is not a birth, but a final spasm of activity. Afterward, the white dwarf fades back into obscurity and resumes its slow journey toward total cooling. Yet the story can become even more dramatic. If a white dwarf gathers too much material from its companion, it can detonate completely in a Type 1a supernova, an explosion so luminous it's visible from adjacent galaxies. Since our Sun is alone, however, its white dwarf is destined for a much quieter fate of gradual fading over trillions of years. Consider also that white dwarfs serve as archives of stellar history. Their chemical makeup holds the secrets of the nuclear reactions that once powered the star from which they formed. By analyzing their light spectra, astronomers can reconstruct the life stories of stars that perished billions of years ago. These stellar remnants are essentially the universe's libraries, each one containing a detailed record of its progenitor star's evolution. allowing us to read the diaries of the dead. Even more astonishing is the fact that white dwarfs can crystallize. As they cool to a specific temperature, the carbon and oxygen inside them will arrange into a rigid crystalline lattice. The final product of this process is a diamond the size of a planet, slowly shedding its heat into the void. Imagine the ultimate destiny of our sun's remnant. After 100 trillion years, it will have cooled to the background temperature of the cosmos, becoming an invisible black dwarf, a cold crystal of carbon and oxygen adrift in a perfectly dark universe. But even that isn't the final word. According to quantum mechanics, after an almost infinite duration of 10 to the 34th power years, even this cosmic diamond will eventually disintegrate into fundamental particles. This time frame is so immense that it defies human comprehension. To put it in perspective, if this entire lifespan were scaled down, the universe's current age would be equivalent to a single second within a period billions of times longer than the cosmos has even existed. This reveals that the white dwarf our sun will become is, for all intents and purposes, an everlasting celestial body, destined to survive not just every other star, but the very fabric of the universe as we know it today. You could think of it as a celestial vessel, preserving the legacy of our star until the final moments of existence. So, you are now aware of the ultimate fate awaiting our sun. Following the turbulent periods as a red giant and a planetary nebula, our star will settle into a serene existence as a white dwarf. This isn't an end, but rather a metamorphosis into an entity with a lifespan beyond our wildest imagination. However, this white dwarf represents far more than a memorial to our sun. It is its enduring inheritance, a gift to the cosmos of the future. Now I want to explain what our star will leave behind, and how its demise will spark new beginnings across the universe. It might appear that the sun's narrative concludes once the planetary nebula fades and the white dwarf starts its trillion-year cooling process. But this perception is mistaken. The truth is, our star's final moments will be a profound act of cosmic generosity, seeding the galaxy with the material to form innumerable new worlds. What I am about to share will fundamentally alter your perspective on the significance of stars in the grand scheme of the cosmos. With the exception of hydrogen, every single atom that constitutes your being was forged deep inside a dying star. The oxygen in the water you consume, the carbon that structures your DNA, and the iron flowing through your veins are all legacies from ancient stars that, eons ago, met the same fate that our sun will one day face. As our star casts off its external layers, it will release into the cosmos all the elements it has meticulously synthesized in its core over 4.5 billion years. This chemical bounty, which includes carbon from helium reactions, oxygen from the fusion of carbon and helium, as well as neon, magnesium, and silicon, will be dispersed throughout the vastness of interstellar space. Yet the story doesn't end there. During the last stages of a red giant's existence, its core becomes a crucible for unique nuclear reactions that forge elements unattainable in stable stellar environments. These processes give birth to rare isotopes that will serve as invaluable cosmic chronometers for future scientists, enabling them to precisely date stars and entire galaxies. Consider the sheer magnitude of this event. Our sun will expel approximately half its total mass into space, an amount exceeding the mass of Earth by more than 1,000 times. This ejected matter contains sufficient raw material to form hundreds of entirely new planetary systems, meaning the end of a single star can herald the beginning for hundreds of new worlds. Now for a development you likely haven't considered. Scientists have found that matter cast off by dying stars doesn't just spread out randomly. On the contrary, it forms intricate interstellar patterns, including waves, bubbles, and shock fronts, which actively guide the formation of the next generation of stars. Consequently, long after its demise, our star will act as a celestial architect, its ejected material dictating the location and manner of new star births for billions of years to come. At this point, the narrative takes on a genuinely poetic quality. You see, included in the material our dying sun will release are the very elements that currently exist here on Earth. The atoms comprising our oceans, mountains, atmosphere, and even all living things, are destined for a grand cosmic voyage to entirely new worlds. Perhaps the most astounding part of this entire saga is the possibility that if humanity, or whatever we evolve into, has achieved advanced spacefaring capabilities, we could actually follow the destiny of Earth's atoms. Picture a future civilization witnessing the very atoms of their ancestral homeworld being incorporated into new stars and planets across remote regions of the galaxy. Get ready for a realization that forges an extraordinary link between the past and the future. Our own sun is composed of matter from long-dead stars. The heavier elements found within it were synthesized in stars that perished long before our sun ever ignited, which means our star is essentially built from the recycled remnants of cosmic history. However, our sun has contributed its own unique creations to this inheritance. Over 4.5 billion years, its thermonuclear furnace has enriched its own makeup with new elements and isotopes. So, upon its death, our star will bequeath to the future not just this ancient stellar material, but also the distinct products of its own existence. You can visualize this as a great cosmic relay race where stars are formed, live out their lives, and upon their death, pass their constituent matter on to the next generation. With each successive generation, stars become more chemically complex than their predecessors, gradually enriching the universe with the heavy elements vital for creating planets and fostering life. This leads to a remarkable insight. Any stars that form from the remnants of our sun will possess a more enriched chemical makeup than our star ever did. This implies that planets orbiting them could feature more intricate geology and a greater variety of minerals, potentially offering even more favorable conditions for life to emerge. Picture for a moment a future world coalescing from the matter our sun has cast out. This new planet might have oceans where the oxygen in its water was forged in the sun's core, and continents built from rock containing silicon born from our star. Its atmosphere could be filled with carbon atoms that once cycled for eons within the sun's convective currents. Should life emerge on a world like this, its inhabitants would be quite literally composed of atoms from our own sun. They would effectively be the far-flung progeny of Earth's matter, dispersed across space by our star's final act. It's a concept akin to a cosmic reincarnation, where the fundamental building blocks of one world are passed on to create another. This represents a genuine form of immortality, not through the persistence of a single entity, but through the transmission of its very substance. While the sun as a star will cease to exist, its physical matter will endure for trillions of years within new worlds. Every atom forged deep inside our star carries the potential to become part of future planets, other stars, and perhaps even novel forms of life. What is truly astounding is the idea that some evidence of our solar system's existence could persist indefinitely. Should humanity ever construct sufficiently massive cosmic objects, their remnants might one day be identified as elemental distribution anomalies by future observers. Consider what is occurring this very moment. Somewhere in our galaxy, new stars are igniting from the remnants of ancient suns that perished billions of years ago. These newborn stars incorporate the legacies of countless predecessors, possibly including those that existed long before our own solar system formed. You and I are part of a ceaseless current of cosmic creation, where the demise of one star sparks the beginning of another. Each successive generation of suns enriches the universe with novel elements, creating new potentials and new worlds. In this context, the death of our sun is not a conclusion, but merely the continuation of this magnificent cycle. Just imagine a scientist in the far future examining a star born from the sun's remains. By analyzing its spectrum, they could deduce that it contains elements typical of a yellow dwarf, and perhaps even infer that a planetary system much like ours once orbited it. This future researcher would essentially be an archaeologist of cosmic history, piecing together the story of long-dead stars from faint chemical signatures. The sun's legacy would then become a subject of scientific inquiry for civilizations that have yet to emerge. It's here that you can grasp the fundamental secret of cosmic inheritance. Absolutely nothing in the universe ever vanishes completely. Every star, planet, and life form imprints itself on the fabric of the cosmos, making death not an erasure, but a transformation into a new state of being. The sun is destined to teach us this final, crucial lesson. On a cosmic scale, there is no such thing as true death. There are only the perpetual transformations of matter and energy, all part of an unending dance of creation and destruction. The story of our sun is therefore more than just the biography of a single star. It is a profound lesson on the nature of existence itself. It demonstrates a universe where every conclusion marks a new beginning, and every death seeds new life on a scale that our minds can scarcely fathom. Our sun was born from the dust of ancient stars, has shone as a beacon of light and warmth for billions of years, and upon its death, it will provide the raw materials for innumerable new worlds. This is not a narrative about finality, but one about an infinite cycle of creation where nothing is ever lost, only reconfigured into new forms. And here, the deepest truth of the universe begins to unfold. The sun's death in 5 billion years is not a catastrophe, but a vital component of cosmic evolution. Without dying stars, there would be no heavy elements. Without heavy elements, no planets could form. And without planets, life as we know it would be impossible. You see, the very existence of intelligent life is predicated on the necessity of stellar death, making mortality a prerequisite for vitality, not its opposite. Every single carbon atom inside your DNA is a tribute to an ancient star that sacrificed itself so that you could exist. Contemplate the sheer scale of this cosmic altruism. Trillions of stars throughout universal history have lived and died just to infuse the cosmos with the elements required for planets and life to emerge. Your own existence is a direct consequence of the sacrifices made by countless suns that burned in nuclear furnaces eons ago. But here is a turn you may not have anticipated. This chain of sacrifice and rebirth will not conclude with the end of our sun. Our star will simply pass the torch to the next generation of luminaries, which will in turn pass it to the next, for as long as matter capable of thermonuclear fusion exists. This presents a paradox. With each generation, stars make the universe more hospitable to life by enriching it with heavy elements. Simultaneously, however, the total number of stars decreases, as the universe's supply of hydrogen is finite. This means the cosmos is concurrently becoming more favorable for life, while growing less capable of sustaining star formation, placing us in a uniquely significant era. We are living in the golden age of the universe, a time when there is a perfect balance of abundant stars and a sufficient supply of heavy elements for complex planetary systems. In the distant future, the universe will be rich in elements but starved of stars, while the distant past was precisely the reverse. This realization profoundly reframes our position in the cosmos. We are not merely random spectators of the universe's history. We exist at the most opportune moment for intelligent life to thrive. In earlier epochs, heavy elements were too scarce, and in later ones, stellar energy will be too rare. Consider the immense responsibility this places upon intelligent life during this golden age. It is possible that we, along with other civilizations, are the mechanism through which the universe achieves self-awareness. Through us, the cosmos investigates its own past, comprehends its own laws, and generates expressions of art and beauty. If that is the case, then the extinction of any civilization represents an irreplaceable loss for the universe itself, and the duty to preserve and advance intelligence becomes a cosmic imperative. This obligation is owed to the trillions of stars that gave themselves for our existence. It is in this light that our explorations gain profound significance. By studying the life story of the sun, we are not just indulging our curiosity. We are fulfilling a mission encoded into us by the very fabric of the cosmos. We are drawn to contemplate the stars because we are forged from their material. And we study the universe because we are its means of self-discovery. So, as you reflect on this, understand that the sun's death in 5 billion years is not a sentence, but a challenge. It presents humanity, or whatever we become, with a time frame equivalent to the entire age of the Earth to master the art of living independently, no longer bound to a single star. The time is approaching for humanity to evolve into a truly cosmic civilization. In that distant future, we might master the ability to shift planets between star systems, or even construct artificial suns. It is conceivable we will uncover methods to extend the lifespans of stars, or perhaps even guide their evolutionary courses, though we may instead discover forms of existence that are entirely independent of stars altogether. Even if our species vanishes long before the sun's final moments, the imprint of intelligent life could endure within the very structure of matter. Future civilizations might one day decipher the chemical signatures of planets and stars, reading the tale of a long-lost species that once grasped the nature of the cosmos. This reveals the principal lesson from the sun's biography. On a cosmic scale, nothing ever truly perishes. Matter and energy simply transition between forms in a ceaseless cycle of creation and transformation. The sun's eventual death will not mark the conclusion of its story, but rather its continuation in new manifestations. The resulting white dwarf will glow for trillions of years, carrying the memory of our star into the distant future, while the heavy elements forged in its core will become the foundational material for new worlds. Furthermore, all the energy the sun radiated throughout its life will forever remain a part of the universe's electromagnetic field, a testament to its enduring influence. This reveals a form of immortality for our star, not because it will shine forever, but because its impact on the cosmos is permanent. Every photon it has released, every atom it has forged, and every planet its warmth has touched is now woven into the eternal history of the universe. And you are an inseparable part of this grand narrative. Your body is constructed from stellar material, and your life is sustained by the energy of a star. More than a mere observer of this cosmic drama, you are an active participant, and astonishingly, a medium through which the universe achieves self-awareness. The sun's life story is therefore your own biography, just stretched across billions of years. The saga of our star is reflected in every atom that constitutes your body, in each breath of air you draw, and in every thought that crosses your mind. You exist within a star, and the star resides within you. Looking ahead 5 billion years, when the sun swells into a red giant and then contracts into a white dwarf, the very matter that makes up your body will commence a new cosmic journey. The atoms that were once you may be integrated into new stars, new planets, and perhaps even new forms of life. In this way, you are also immortal, an enduring component in the perpetual flow of matter and energy throughout the universe. Now, with this understanding of the sun's complete life story, you can view our star with entirely new eyes. It is far more than a source of light and heat. It is both your cosmic ancestor and your descendant. The sun gave you life, and in turn, you give it meaning by studying its history and comprehending its place in the cosmos. So, every morning when you feel the sunlight, remember what it truly is. It is not just radiation from a distant celestial body, but a message from the thermonuclear heart of the cosmos. It serves as a reminder that you are part of the greatest story imaginable. The story of the universe coming to know itself through conscious beings like you.